Hello and welcome to another calculus video. In this one, we're going to look at section 7-7, Indeterminate Forms and L'Hopital's Rule. We are jumping forward to chapter 7 in the book. This has recently become fair game on the AP test for the AB calculus classes. It's always been on the BC exam. This we are going back to take a look at something in limits. Let me back up here. The assignment for this section, page 511 in the book, there's 3 problems you're going to do on paper. The majority, 7 of them, are on WebAssign. Now here are some limits. Notice we are heading to infinity, and we have a fraction. If I try direct sub, I'm going to get infinity over infinity for any of these if I do direct substitution. Now, the way we looked at it in the previous section was I called it the power struggle between the numerator and the denominator. Here, the numerator was more powerful, so that limit was headed to infinity. Here, we had a tie, and we could just use the leading coefficients in the form of a fraction. If the denominator was more powerful, that limit was 0. Now that's all well and good if you have 2 polynomials in a fractional form. Polynomial numerator, 1 in the denominator. That trick will work. But what about if we have a transcendental function like sine or cos or e to the x? We cannot do that trick, so we need another way to figure out these limits when x is heading out to infinity. And that's going to be coming from L'Hopital's rule. So here we've got 2 bullet points. Recognize limits that produce these indeterminate forms and apply L'Hopital's rule to evaluate a limit. And it says, recall that the forms 0 divided by 0 and infinity over infinity are called indeterminate because they do not guarantee that a limit exists, nor do they indicate what the limit is, if one exists at all. When you encountered one of these indeterminate forms earlier in the text, you attempted to rewrite the expression with various algebraic techniques. Remember what before we figured out the shortcut, we would divide the numerator and denominator by the highest quantity or highest power in the denominator, or here we just did a little long division, and we would try to get it down so we could just do direct sub and then figure out the limit. Like here, direct sub would not work in this one. But if we actually do the division, if we divide the numerator and denominator by x plus 1, we get a different looking function that direct sub did work on. Same thing here. If we try direct sub there, you'll get infinity over infinity. We divided through by the highest power in the denominator. Direct sub worked the second time, giving us our limit of 3/2. Occasionally, we can extend these algebraic techniques to find the limit of transcendental functions. For instance, here at e to the 2x minus 1, the numerator can be factored into e to the x plus and minus 1. Denominator e to the x minus 1 will cancel, leaving just e to the x plus 1, and then direct substitution worked. So that happens from time to time, but the function has to be something that you could factor and cancel. Now, not all indeterminate forms, however, can be evaluated by algebraic manipulations. This is often true when both algebraic and transcendentals are involved. For instance, here our limit is headed to 0, e to the 2x minus 1 over x. This produces 0 divided by 0. We could rewrite the expression by breaking it into 2 separate fractions. Merely produces another indeterminate form, infinity minus infinity. Of course, we could use technology to estimate the limit as shown in the table down here below. We could plug that into our TID9 or from the graph over here. This limit, we will see it verified in example 1. But if we look at the table here, it looks like what goes right in between there, it looks like it's going to be 2. Also on the y-axis, there's our graph, but it's got a hole in it right there at 2. I'm suspicious that the answer is going to be 2. L'Hopital's rule. Now it says to find the limit illustrated in figure 711, that's this one here. To find that limit, we can use a theorem called L'Hopitals Rule, named after the French mathematician Guillaume L'Hopital back in the 1700s. And now that I look at it, he only made it to 33 years old. No, 43 years old. 43. This theorem states that under certain conditions, the limit of the quotient, f of x over g of x, is determined by the limit of the quotient of the derivatives. When we were finding derivatives, when we first saw a fraction, I said you can't just derive the numerator and denominator and keep them separate. We figured out the quotient rule. This is not the quotient rule. We are trying to find a limit, not a derivative. So we can just derive the numerator, and then we can just derive the denominator separately and try direct sub again. Now, to prove this theorem, which we're not, we could use a more general result called the extended mean value theorem. And this theorem just says we have two functions, f and g. F is the numerator function, g is the denominator function. If they are differentiable on the interval and continuous on that same but closed interval, such that the denominator is not going to equal 0 when we derive it, for any value in that interval, then there must exist a point C somewhere in the interval such that f prime c over g prime of c is equal to f of b minus f of a over g of b minus g of a. A proof, if you're curious, is in the back of the book in Appendix A. But here is L'Hopitals Rule. Let f and g be functions that are differentiable on the open interval a to b containing point c, except maybe at point c itself. Assume that the denominator's derivative is not going to equal 0, except possibly maybe at that point c itself. If the limit of f of x divided by g of x as x approaches c produces the indeterminate form 0 over 0, then the limit as we approach c of f of x over g of x is exactly the same as f prime over g prime. Derive the numerator and denominator separately and try direct sub again. This result also applies when the limit of f of x over g of x as x approaches c produces any of these indeterminate forms. So 0 divided by 0 is a biggie, and also infinity over infinity. Now, this also works for negatives. I could put a negative infinity in the numerator. Oops, where did that go? Oops, I guess. There we go. I could have a negative infinity in the numerator, or the negative infinity could be in the denominator. They could both be negative infinities. It doesn't matter. Here's infinity over infinity, negative on top, negative on bottom, or both negative. 0 over 0 and infinity over infinity is what we're looking for that we might apply L'Hopitals Rule. Now, people occasionally L'Hopitals Rule incorrectly by applying the quotient rule. Be sure you see that the rule involves f prime over g prime and not the derivative of that quotient. L'Hopitals Rule can be applied to one-sided limits. For instance, if the limit of f of x over g of x as we approach c from the right produces the indeterminate form 0 over 0, then we can just apply L'Hopitals Rule to that one-sided limit, provided that it does exist. What's this? Indeterminate forms and L'Hopitals Rule are tested on both versions. The year we got our new textbook with the AP angle on it, that was the first year, so here they are telling us that this is on both AB and BC exams. Here we go, finally, example 1. We have come across a limit out in the wild. We're approaching 0. E to the 2x minus 1 over x. If we try direct sub, we're going to get e to the 0, which is 1 minus 1 over 0. So we do get the indeterminate form 0 over 0. So we are going to apply L'Hopitals Rule. 0 over 0 is one of the ones that it works on. So we are going to derive. It's still going to be a limit as we approach 0. Let's derive our numerator. E to the 2x, we derive that. It's going to be to the e to the 2x, and we're going to chain rule and get another 2 in there. And the minus 1 will derive away. And if we derive the denominator x, that just becomes a 1. Ooh, that's good. We're not dividing by 0. So let's try direct sub again. 0 goes in for x, so that becomes e to the 0, which is 1, times that 2 is 2. So our limit is 2. Excellent. Now what's this down here real small? In the solution to example 1, note that you actually do not know that the first limit is equal to the second until you have shown that the second limit does exist. In other words, if the second limit had not existed, then it would not have been permissible to apply L'Hopital's rule. Another form of L'Hopital's rule states that if the limit f of x over g of x as x approaches infinity or negative infinity produces the indeterminate form 0 over 0 or infinity over infinity, then these are the same. The limit as we approach of the original function f of x over g of x is the same as if we derive those numerators and denominators exist, provided that the limit on the right exists at all. Okay, example 2. If we try direct sub, now they kind of spoil it up here. They tell us the indeterminate form. If we put infinity in, we're going to get the ln of infinity, which is infinity. Remember, the natural log graph looks like this. As we head out toward infinity, we are heading up also toward infinity. And denominator direct sub the infinity in. So direct sub gives us infinity over infinity. That is our indeterminate form. L'Hopital's rule can be applied. So we're going to keep our limit notation. And we're going to derive the numerator. Natural log of x derives to 1 over x. Denominator x derives to a 1. So this just becomes the limit as x heads to infinity of 1 over x. Direct sub did not work at the beginning, but if we try direct sub now, we get 1 divided by infinity and a finite 1 numerator divided by an infinitely huge denominator is heading for 0. So that limit is equal to 0. That's nothing. Use a graphing utility to graph the natural log of x, that's the numerator, and the denominator x in the same viewing window. Which function grows faster as x heads toward infinity? How is this example related? Well, I guess if we looked at the graph, again, the natural log of x goes through the point 1 comma 0 and heads up like this. Y equals x is just a line going through the origin up diagonal through the graph paper grid. So here when we look at it graphically, we see our denominator is heading to infinity faster. So it is more powerful, and that's going to head our limit down to 0 like we just saw. All right. What's next? Example 3. Ooh, there it is. Occasionally, it's necessary to apply L'Hopital's rule more than once to get rid of that indeterminate form. So here is our limit in its natural state. If we try direct sub, negative infinity is going to go up here and be squared. So that's going to be positive infinity. And if we put the negative infinity up here in this exponent, that's going to be e to the negative infinity. So that is e to the infinite power. That is also heading to infinity. Because remember, e looks like this. So as we're heading out toward infinity, we're heading up also toward infinity on our y-axis. So we are in a form that L'Hopital's rule can be applied. So we are going to derive the numerator. That's the easy one. X squared derives to 2x. Denominator e to the negative x will derive to itself, but we are going to chain rule a negative 1 when we derive our inner function. So here's our derivative. Let's try direct sub a second time. So negative infinity goes up top. We're going to have 2 times negative infinity, and that's negative infinity. When we plug negative infinity in here, we're going to have negative e to the positive infinity. So that's going to be negative e to the positive infinity, that is also going to be heading for negative infinity. So here our answer is slightly different, but it's still in a form that we can apply L'Hopital's rule. Let's apply again. I'm going to switch to blue ink. So we're heading still to negative infinity. If we derive the numerator, 2x derives to 2. Denominator e to the negative x, negative e to the negative x, will derive to itself. We'll have another negative from the chain rule, making it back to a positive e to the negative x. Now, if we try direct sub one more time, negative infinity has no place to go in the numerator. That's going to stay at 2. Down here, e to the negative infinity is going to be e to the positive infinity or infinity. Aha! Now this is something that has an answer. 2, a finite numerator, divided by an infinitely huge and growing denominator, is heading for 0. You may notice a lot of answers for these limits are 0, maybe 1. On a test or homework, I always look at the work. I've seen students whose work, devolves into a bunch of scribbles that's hard to read, and then at the end they write a real big equals 0. The limit is 0. I got to see the work that got you to that answer, because 0 as a limit is a great guess. Up next, not example 4 yet. In addition to 0 over 0 or infinity over infinity, there are other indeterminate forms such as 0 times infinity, 1 to the infinite power, infinity to the 0 power, 0 to the 0 power, and infinity minus infinity. For example, consider the following 4 limits that lead to the indeterminate form 0 times infinity. Here, the limit is going to be equal to 1. Here, the limit's going to be equal to 2. Here, it's going to be equal to 0. And then here, it's going to be equal to infinity. And it says because each is different, it's clear from the form 0 times infinity, it's indeterminate in the sense that it does not determine the value or even the existence of the limit. The remaining examples in this section show methods to evaluate these forms. Basically, you attempt to convert each of these into 0 divided by 0 or infinity divided by infinity so that L'Hopital's rule can be applied. Notice we can only apply L'Hopital's rule if it is in the form of a fraction. Sometimes the question that they give you is not even in the form of a fraction. But if you do get one of these indeterminate forms up here, we can play around with it and turn it into a fraction, and hopefully L'Hopital's rule will able to be applied, as we may see here in example 4. So evaluate. X is heading to infinity, e to the negative x times the root of x. Oops. So we are going to try direct sub. And infinity is going to jump in there. That's going to be e to the negative infinity. There we go. E to the negative infinity times the root of infinity. Let's see. Well, we'll forget that. So remember, e to the negative x looks like this. Negative exponents go downhill. So as we head out toward infinity, that is going to head us for 0 times the root of infinity is still infinity. When you square root it, it's going to slow it down, but it's going to keep marching toward infinity. So direct sub gave us this form 0 times infinity. It's not in any form that we can use. Let's see, go back to the original here. Can we rewrite it? The first thing that jumps out at my eye is that e to the negative x. What can we do with negative exponents? Well, we can move them downstairs and make the exponent go positive. So e to the negative x in the numerator becomes e to the positive x in the denominator, and we're going to leave the root of x alone. So now at least it's in the form of a fraction, and we can try direct sub again. So now the square root of infinity is infinity. The e to the positive infinity is also equal to infinity. So another indeterminate form, but we can apply L'Hopital's rule. It's in that form, infinity over infinity. So let's derive the limit as x heads to infinity. The square root of x, or x to the half, becomes 1/2 x to the negative a half, so it's going to look like that. And then e to the x derives to itself. So we got it in a form that we can apply L'Hopital's. We have applied L'Hopital's. Let's see if direct sub helps. So this is going to become a square root of infinity. That's still infinity. Times 2 is still infinity. So what we have here is 1 over infinity. And that's going to turn into a 0. And then e to the infinite power, e to the infinity, is infinity. 0 divided by infinity, not so good. Oh, excuse me. 0 divided by, 1, or excuse me, if that was a 1 or a 2, it's a finite numerator. Same thing here, it's finite, it's 0. An infinitely large and growing denominator. Our limit is heading for 0. Now, I do have in my notes, I don't know if I got this from the book, I'm not sure, but if we go back up to here, another thing we could do is make this e to the x over 1, and we could bring it up and flip it, or we could sort of slide the top fraction off and combine our denominators. Either way, another representation of this would be 1 over 2 e to the x root x. So we could just manipulate what we have here into this form, and L'Hopital's rule will still give us a good answer. If we try direct sub, infinity goes in. That's going to be a 1 in the numerator. And then down here, 2e to the x is going to be infinite, times root of x, that's also infinite. So that would be on an infinite denominator. 1 over infinity is the same thing as 0 over infinity. Okay, what's this numerical solution hiding down here? So we could just do it on a table. Use the table feature on a TI-89 ask mode to evaluate y sub 1 for increasing values. So here our y editor would be our function, and we could start plugging in bigger numbers, 1, 10, 100, 1,000, and you see very quickly we do tend to 0. Okay. It says, when rewriting the limit in one of the forms of 0 over 0 or infinity over infinity does not work, try the other form. For instance, in example 4, you can write the limit as, here they left e to the x negative x in the numerator and move the root x downstairs, which yields the indeterminate form 0 over 0. As it happens, applying L'Hopital's rule to this limit produces this, which also yields the indeterminate form 0 over 0. The indeterminate forms 1 to infinity, infinity to the 0 power, 0 to the 0 power, arise from limits of functions that have variable bases and variable exponents. When you've previously encountered this type of function, we used logarithmic differentiation to find the derivative. We can use a similar procedure when taking limits, as we are going to see in the next example. So here in example 5, we are approaching infinity. And if I plug infinity in there, I'm going to have 1 plus 1 divided by an infinitely big denominator is heading for 0. So that becomes a 1 plus 0, and x is heading for infinity, and that's also our exponent. So we do get 1 to the infinite power. So this is an indeterminate form that we know we might be able to apply L'Hopital's rule to. Now, here is how these problems begin. The big problem is that variable in the exponent. So we're going to say this limit does exist and it's equal to y. So we're going to say y is equal to the limit as x heads to infinity. 1 plus 1 over x to the x power. Now, why do we assume it exists and it's equal to y? So we can do this. I'm going to take the natural log of the left side, and that's perfectly legal as long as I take the natural log of the right side. And I am going to squeeze it in here, the natural log of this side. Now, the reason we're doing this is so we can apply properties of logarithms and bring this exponent down. It's given us trouble while it's up here, so we're going to bring it down and put it in front of the natural log. So the natural log of y is equal to the limit as we head x off to infinity of, and let me go back to a different color ink, x natural log 1 plus 1 over x. Okay, we've done a little bit of manipulation. We could try direct sub again, and if I put infinity in there, this x becomes infinity. And then we're going to have the natural log of, when I put infinity under this 1, it's going to become a 0. So that's just going to be the natural log of 1, and the natural log of 1 is 0, because that's where ln crosses the x-axis. So we've gone from one indeterminate form to another indeterminate form, infinity times 0. So let's see what we can do with this. Okay, so we need to put on our algebra thinking caps. Imagine this is a division line. We do have to get this in the form of a fraction for L'Hopital's to work. What can I move to the denominator? Well, this x, if I move it down, it's going to become x to the negative 1, or let's write it as 1 over x. Same thing. Let's leave the ln of 1 plus 1 over x up here alone. There we go. Okay, at least now it is in the form of a fraction. And you know we need it in the form of a fraction for sure for L'Hopital's rule. Let's try direct sub again. Every little manipulation, let's try direct sub. So infinity goes in, that's going to become the ln of 1, which is 0. Infinity goes in here under this 1. 1 over infinity is also 0. So we're getting closer. This is 0 divided by 0. So L'Hopital's rule can be applied. 0 over 0. I'm going to just put lops, exclamation point. We can use L'Hopital's rule. 0 over 0 or infinity over infinity. We can now derive equals. Okay, let's see here. I'm going to do a division line like this. Now, I'm going to do my numerator in blue. And let me get rid of this. That's sort of getting in the way there. In blue, how do we derive natural log? Remember, it's u prime over u. This is what we are logging, so it will go downstairs, 1 plus 1 over x. And what is the derivative of that? Well, the 1 over x, that's x to the negative 1. And if we derive x to the negative 1, we get negative 1 x to the negative 2. So it's going to be negative 1 over x squared. Now, in red, down here in the denominator, if I derive 1 over x, that's x to the negative 1, that becomes the same negative 1 over x squared. There we go. Now, it might be hard to see here, but we can cancel. I guess the easiest way to look at it is if we bring that red denominator up, flip, and multiply. So if I bring up this red denominator, and now it's x squared over 1, and it's also negative. It's going to cancel with this numerator. You know, those are just going to turn into a 1. Or another way to look at it, and this is the way I have it in my notes, you know, this numerator here, get down there. Why is that not? Nope. Dang it. There it is. I could sort of slide this off of that numerator. So there's kind of a 1 left up there. And now since it's off the top of the fraction, you can see the cancellation this way. Either way, you know that negative 1 over x squared is going to cancel with itself. So what we're left with is the natural log of y equals, ooh, and I dropped my limit notation. The limits as x heads to infinity, 1 over 1 plus 1 over x. Where did I drop my limit notation? So, we've applied L'Hopital's rule. Let's try direct sub. Infinity goes in for x. The numerator stays a 1. There's no x up there. Infinity right here is going to make that 1 over infinity or a 0. So that becomes 1 over 1. So that limit is equal to 1, or so you would think. If this was on the AP test, the first multiple choice decoy answer would be the limit equals 1. Remember, way back to the beginning of the problem, we started with the assumption that the limit exists and it's equal to this. So we're almost done, but not quite. We have the ln of y is equal to 1. So how do we get rid of that natural log without hurting the y? Well, we base e. So e and natural log cancel, and we're left with y equals e to the first, or just y equals e. There's our limit. That's the limit that we're looking for. That would not be the first multiple choice answer. Okay. So remember at the end, we do make that assumption about logging both sides. And here we can also see it in its graphical form, 1 plus 1 over x quantity to the x power. The limit of that, as we head to infinity, is e. So on the y-axis, that's about 2.72 dot, 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 just like pi. That would be our horizontal asymptote. Okay, that was a pretty juicy example. We got 2 more to go. Example 6 here is almost as juicy, or maybe just as. L'Hopital's rule can also be applied to one-sided limits, as we are about to see. So now here we have another variable exponent. We are approaching 0 just from the plus side, from the right, of sine x divided by x. So we try direct sub, of course, sine of 0 to the 0 power. Well, the sine of 0, that's your y-coordinate, and at 0 rads, it's 0. So this is 0 to the 0 power. It's indeterminate form, but not one of them we can use L'Hopital's rule on yet. So just like the last one, we are going to assume that the limit exists, and it's equal to y. And sine x to the x power. And the reason we assume that the limit exists and it's equal to y is so we can natural log both sides. So we give her the old ln treatment, and this is going to be equal to, we can bring this exponent x down, and I'm going to put it in front of the log. So we've got the limit as we approach 0 of x natural log sine x. Okay, let's, I guess, try direct sub again. Every little maneuver, we can always try direct sub. Now here, L'Hopital's rule only applies in fractional form, but we can make sure we're on the right track. So if we plug in 0, this x is going to turn into a 0 times the sine of 0 is 0, and the ln of 0 is negative infinity. Remember now, ln of 0, here's our natural log graph. And as we're approaching 0 from the right, the graph is heading down, down, down to negative infinity. That's why this one had to be a one-sided limit. So there's 0 times negative infinity. It's something we can work with. Let's see if we can get this now in the form of a fraction. So the limit is still there. We are still approaching 0 from the right. But imagine this is a division line. And I want to move something down there. Well, let's move x down there. Down here, it's x to the negative 1, or 1 over x. And we will leave our natural log of sine x upstairs. Okay, we did a rewrite, or any algebra, and let's try direct sub again. So if we plug in 0, we're going to get the sine of 0 is 0, the ln of 0, that is still negative infinity. And now as we approach 0 from the plus side, now remember this is a finite numerator, but now our denominator is getting infinitely small, not infinitely big. We're approaching 0, so this is going to get very, very tiny. That's heading to positive infinity. So any form of infinity over infinity, it doesn't matter where the positives and negatives are, means we can now apply L'Hopital's. We are in a form, use lops, exclamation point, smiley face. Well, that didn't work out so well there. Oh, why do they keep, forget it. Smiley face, you get the idea. So it is time to derive. Let's see. The derivative of natural log sine, remember u prime over u, what we are logging is our denominator. Derivative of sine is cos. That's going to go right up on top. And the derivative of 1 over x, or x to the negative 1, is negative 1 over x squared. Now, we could turn that numerator cos over sine into cotan, or we could just leave it as is. We can just direct sub the 0 in there right now. So if we try direct sub, we're going to get upstairs. The cos of 0 is 1. Down in the denominator, the sine of 0 is 0. As we approach that, that is going to head for infinity. And then down in our denominator, when we approach 0 down there, again, this is a finite 1 numerator divided by an infinitely shrinking denominator. That's heading to negative infinity. So we're on the right track. It sounded like our negative sign moved places. And let's, for the sake of this next step, let's go back and rewrite that cos over sine as cotan. I'm going to get rid of this, and I'm going to make that into cotan. Because L'Hopital's rule gave us another form. After we used L'Hopital's rule, we were still in a form that we could use L'Hopital's. So let's see here. What can we do with this? We could either derive it again or try some algebraic manipulation. Instead of deriving, let's try to flip stuff around. So we're still going to be approaching 0 from the right. But if I bring the denominator up and flip it over, now up in the numerator, it's going to be negative x squared. And up here, this is cotan over 1. If I take it down, it's going to be 1 over cotan, which is tan. Okay, so here we didn't derive anything. It was in the form we could have. But let's just flip things into a different looking fraction and see how that works. Okay, let's do direct sub. 0 goes in, negative 0 squared is 0. 0 goes into tan. Remember, graphically, tan goes through the origin, so the tan of 0 is 0. So we're still in a form of indeterminate, something that L'Hopital's can be applied to. So 0 over 0, let's try deriving. Let me switch to red ink. Numerator's easy. Negative x squared derives to a minus 2x. Tan derives to secant squared of x. Okay, so we tried L'Hopital. We did some deriving. Let's try direct sub. 0 goes into the numerator. Negative 2 times 0 is just 0. Okay, that's not the end of the world. As long as we don't have a 0 downstairs, we're going to be okay. And now let's see here, secant squared of 0. I'm thinking back, that's the same as 1 over cos squared at 0. The cos at 0 is 1, so that becomes 1 squared or 1. So that's just 1 over 1. 1. Okay, we made it. That is equal to 0. Again, if you're on the AP test, and this is multiple choice, that would be multiple choice answer A, and some people might jump right on it, circle it, and move on. But think back to the start of the problem. Our limit is not 0. The ln of y is equal to 0. Okay, how do we get rid of that natural log without messing up the y? We base e. Base e. So now we get y equals e to the 0. Anything to the 0 is 1. So there's our limit. Again, a lot of limits are zeros and ones. On a problem like this on a test, I would go back and look at your work. It'd be real easy to just devolve into algebraic scribbles and to write real big and proud y equals 1 when you actually had no idea what was going on. What's this? When evaluating complicated limits like the one we just saw, it's helpful to check the reasonableness of the solution with a graphing utility. For instance, the calculation in the table and the graph in the figure below are consistent with the conclusion of sine x to the x power as approaches 1 as we approach 0 from the right. So here's our graph. We can approach the y-axis from the right and see that the height of that is going to be about 1. Okay, what is in store for us next? Our last example. Another indeterminate type form. And they are, again, once again, spoil the surprise. This one we tried direct sub. Excuse me, we are going to get infinity minus infinity. So if we try direct sub, this is going to be not the ln of 1, but we're going to approach the ln of 1. So we're going to be approaching 0. 1, an infinite or a finite numerator 1 by an infinitely small denominator is heading for infinity. And then here, if we approach 1 from the right, think 1.1, we're going to have a positive numerator, a positive denominator. That means we're heading to positive infinity. So here we are, infinity minus infinity is an indeterminate form. But do not panic. We will find our way to LHopitals Rule, and then Mr. L'Hopital shall save us. But what can we do to this? It's not in L'Hopital form yet. Well, I see a fraction minus a fraction. Let's combine the fractions. Denominator is just going to be the ln of x times that quantity x minus 1. Now let's fix up our numerators. This numerator 1 is going to get multiplied by the x minus 1 quantity. Now be careful here. This next numerator is a negative 1, and that's going to be multiplied by the natural log of x. So here is our function now written in a different looking form. It's in the form of a single fraction. So let's try direct sub. So if I put a 1 in there, I'm going to do my scratch work up here. 1 minus 1 is 0, minus the ln of 1, which is also 0, so 0 minus 0 upstairs. Here we're going to have 0 times 0. It's the same quantities, but downstairs we're multiplying. So we have 0 minus 0 over 0 times 0. Either way we look at it, it's 0 divided by 0. And that is good news because L'Hopital might be of help. So let's see. We're going to need to derive. So if I derive across this numerator, this first term here, x, that's going to derive to a 1. The minus 1 derives away. And then we have minus the ln of x derives to 1 over x. Down in the denominator, we're going to have to do product rule. Let me switch to black ink. So we've got the first ln of x times the derivative of the second. The derivative of the second would be a 1, plus the second thing, x minus 1, times the derivative of the first. Derivative of natural log x is 1 over x. Okay, there we go. Now, I really don't feel like direct subbing a 1 in there just yet. What I would like to do is clear all the fractions. Notice we have a fraction in numerator and denominator, and that denominator in our fraction is just an x, so I'm going to distribute an x in the numerator. And of course, you know we have to be fair. We're going to distribute the same x in the denominator. So let's see here, we distribute, we're going to get x minus x over x is 1. Numerator looks a lot cleaner now. Now in the denominator, we're going to distribute here, so that's going to be x natural log of x. Now be careful, notice here this is one big term. So if I distribute x to it, I'm just going to put it right up here, so that's going to be x divided by x. That turns into a 1, so we're just left with plus x minus 1. Okay, So there, remember now we derived top and bottom, but using L'Hopital's, but we have not direct subbed to see if it worked. Now let's try. Distribute or sub the 1 in there. 1 minus 1. Numerator is 0. Remember, it's not the end of the world. Let's see what happens in the denominator. We're going to have this is going to be the ln of 1. That's going to turn into a 0 and wipe out this x. So that's a 0. Plus this x turns into a 1. And then we have minus 1. So bad news, it is 0 divided by 0. But I guess the good news is it's still in the form that we can do a L'Hopital's rule. We can derive this again. All right, let me move this up. Keep my limit notation. Derive the numerator. This x is going to derive to a 1. The minus 1 is a constant. It derives away. Here, let me switch to blue ink for the product rule. We are going to product rule this. So we have the first thing times the derivative of the second plus the second thing times the derivative of the first would be a 1, so I'm not going to write it in there. And then the derivative of this plus x will be a plus 1. And then the minus 1 derives away. So we're getting there. We're getting there. Before we direct sub, we can do a little cleaning up here. The limit as x approaches 1 from the right. Numerator is a 1. Here we have x times 1 over x. That's just going to be x over x, so that turns into a 1. We combine it with this one and make that a plus 2. And then we've got this natural log of x, ln x. Okay, we L'Hopital'd. We did some combining. Let's direct sub and see if we're done. So, numerator's a 1. Here the 1 jumps in. Natural log of 1 is 0. 0 plus 2 is 2. The limit is 1/2. Now remember, that's not the ln of something equals a half. We did not make that assumption to start this problem. Here we just ground it out until we got that limit. Limit is 1/2. And that is, I guess that's not the last example. We've got a little talk about here. The forms, 0 over 0, infinity over infinity, infinity minus infinity, 0 times infinity, 0 to the 0 power, 1 to the infinity power, 0 to the, or infinity to the 0 power have been identified as indeterminate. There are similar forms you should recognize as determinant. Infinity plus infinity is always infinity. Infinity minus infinity is like adding a negative infinity to it, so those will add up to a negative infinity. 0 to the infinite power is 0. 0 to the negative infinite power is infinite. As a final comment, remember L'Hopital's rule can be applied only to quotients leading from indeterminate forms, 0 over 0, infinity over infinity. For instance, the application of L'Hopital's rule as shown here is very incorrect. Let me just make this a little bit bigger. So we've got our limit as x approaches 0 of e to the x over x. Notice here they put is exactly equal to this limit. They derived the numerator, e to the x. They derived the denominator into a 1. And they say that that limit then would be equal to 1. But let's see what happens if we plug in the 0 to begin with. If we plug in 0, we get e to the 0. E to the 0 is 1. Divided by, when we direct sub in there, that would be 0. So this would originally, with direct sub, this would give us 1 over 0. So we could not use L'Hopital's rule. L'Hopital would have been very disappointed if we had tried. It wasn't in the proper form to get started with. Blah, 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 blah. All right, that's it. Next time we are together, we'll work on some of the odd problems from the exercises that will help with the homework. I will see you then.